Hey guys, welcome to the Raptors, a digital platform of the RAPT Excellent Tutorials. Today we are going to discuss expected questions which may turn up in CBSE board exam 2026 of physics. So we are going to discuss expected question for physics. The exam is scheduled on 20th February, that is Friday. The expected questions that we have is so we'll go chapter wise, like we'll start from chapter 1 and then we'll go through each chapter, and then the first question is from electrostatics, so I'll mark it electrostatics. Now the type of questions which may turn up is uh, to find null point. In this type of problem, you will be given two point charges q1 and q2. They are separated by a distance r, and you need to find the null point, that is the point where the net electric field is 0 or net force is 0. So if these two charges are of same kind, if both of them are positive, then the null point will be between these two charges. Okay, if the charges are of opposite kind, suppose this is positive and this is negative, then the null point will be either uh, like beyond B or beyond A, depending upon the magnitude. So if Q1 has higher magnitude, then the null point will be on the side of Q2, that is beyond B. If Q2 is negatively charged and has greater magnitude, then null point will be on this side, because Q1 will try to push a test charge. How to find out the null point? Suppose consider a test charge here, and we imagine that the Q1 is positive and Q2 is negative. So Q2 is going to push this charge along this direction and Q1 is going to pull. So the forces are opposite. So when the forces will balance, the idea is to find the point where the forces are in the opposite direction and are equal in magnitude. Alright, assuming the charges are of same kind, let C be the point where the net force is 0. That means we consider a test charge here on which the force due to Q1 charge will be along this direction, that is F1, and then force due to Q2 will be along this direction, that is F2. So the net force on Q0 should be 0. Now let this point C be at a distance x from the point A, then the rest of the distance becomes r minus x. So for this point to be a null point, magnitude of F1 should equal to magnitude of F2. That means A Q1 Q0 by x square must equal to K Q2 Q0 by r minus x whole square. So what you need to do, just solve it. Q0 gets cancelled, so you have Q1 by x square equal to Q2 by r minus x whole square. Now if you are given the values of Q1 and Q2 and r, you can find x, and by finding x you can find out the null point. So the value of x will be your null point. So guys, we'll take an example and solve this question. Let us take an example. Suppose Q1 here is 1 coulomb, Q2 is 2 coulomb, and the distance between them r is 1 meter. So we need to find point C, which is at a distance x from Q1, where there is a null point. So we'll put these values in equation 1. So equation 1 becomes 1 by x square is equal to 2 by 1 minus x whole square. I will cross multiply. So this will become 1 minus x whole square equal to 2x square. If you take square root, the easiest thing will be to taking square root. So it will be, or you may expand it and then solve the quadratic equation. Either way, you'll get same solution. So expanding it gives you 1 square x square minus 2x equal to 2x square. We'll take this x square that side, so it becomes x square plus 2x minus 1 equal to 0. Now it is a quadratic equation, and the value of x will be minus 2 plus minus minus 2 square, no, plus 2 square minus 4ac divided by 2a. So the value becomes minus 2 plus minus 4 plus 4 divided by 2. So it comes out to be minus 2 plus minus 4 plus 4 is 8, which is 2 root 2 divided by 2. So take 2 common, and this comes out to be minus 1 plus minus root 2 by 2x. Now you see, since the charges are of same kind, we have chosen the charges to be of same kind. The null point hence will be between the charges, because if the charges are of same kind, the charge q1 will force test charge in this direction, and q2 will force it along that direction. So the distance cannot be negative, assuming this to be origin. The distance will be positive. So we take x to be minus 1 plus root 2 by 2. If you put the value of root 2 minus 1 plus 1.414 divided by 2, so it is 0.414 divided by 2, so it comes out to be 0.207 meter. So the null point or the balance point is at a distance of 0.207 meter. So the second kind of problem which may turn up in your exam is, there are two metallic spheres. You may assume them to be identical. Suppose there are two identical metallic spheres of mass m, which has charge q on it, and then other sphere is lying on floor, and it is right below this, right below the first sphere, and it also has got charge. Assume this is q1 and this is q2. Now to maintain the first sphere A suspended in air, how much charge the second sphere B should possess or should have, so that the first sphere is suspended in air, right? So what forces are playing, are coming into play here? Since this sphere A has mass m, it will have gravitational force pulling it downward, but this second sphere is having the same kind of charge, so it will repel it, and then there will be electrostatic force of repulsion. So the sphere A will be floating, or it will be suspended in air. It will be in equilibrium if these two forces are in equilibrium. So we have electrostatic force must equal to gravitational force. So k q1 q2 by r square. The distance between these two spheres is h. Let's say h. So k q1 q2 by h square must equal to mg. So you can find q2 on this chart. So q2 will be mg, h square will get cross multiplied divided by k into q1. Now we can take an example. Suppose, let us take values. Let m is equal to 2 kg, q1 is equal to 2 coulomb, h is equal to 1 meter. We are taking very normal values, and g is equal to, let us take approximately, let it be 9.8 only meter per second square. Now we need to find q2. Therefore q2 will be 2 into 9.8 into 1 square divided by 9 into 10 to the power 9 into q1 is 2 coulombs. So this gets cancelled, and you have q2 to be equal to if you divide 9.8 by 9, so it will be 1.09 10 to the power minus 9 coulomb. So Q2 must have 1.09 10 to the power minus 9 coulomb to be so that the sphere A is maintained in equilibrium. So this is another kind of problem which may turn up in your exam. The third kind of problem which may be asked in your exam is to find total electric field or total force on a charged particle which is placed at the one of the vertices of an equilateral triangle. Suppose this is an equilateral triangle and you have charges. Suppose you have a q1 here and minus q2 here. So electric field, you want to find electric field at point A. So electric field due to charge at B, which is charge q1, it is positive, so electric field will go outside, so it is E1, and for this it will be directed towards C, so it is E2. Since it is an equilateral triangle, this is 60 degrees and these two angles must make 180 degrees, so this is 120 degrees. Now we have two vectors E1 E2, so E1 and E2, the angle between them is 120 degrees, so the resultant will be E, which is given by the magnitude of E is given by E1 square plus E2 square plus 2 E1 E2 cos theta. Theta here is 120 degrees. Alright, so the resultant should look like this. Let this resultant makes an angle beta with E2. So we need to find the magnitude of E and then angle it makes with one of the vectors E2. So the magnitude E is given by this formula. Now you know theta here is 120 degrees, so cos of 120 degrees is 1 by 2. So it is important to keep in mind that cosine of 120 degrees is half, minus half. The angle beta, this angle beta will be given by tan beta will be given by E1 sin 120 divided by E2 plus E1 cos 120 degrees. Now sine of 120 degrees is root 3 by 2. So this to keep in mind. I will take an example. Let us Q1, for example, let us Q1 be 1 coulomb, Q2 is minus 2 coulomb, and A, the distance, the side of the equilateral triangle is 1 meter. Therefore, the magnitude of the electric field will be, now for this your E1 becomes K Q1 by R square. So in this case 9 into 10 to the power 9. Q1 is 1 coulomb by R is your 1 meter. So it becomes 9 into 10 to the power 9 Newton per coulomb. E2 will be K Q2 by R square. So it is 9 into 10 to the power 9. 2 divided by 1 meter whole square. So it becomes 1.8 into 10 to the power 10 Newton per coulomb, or for the simplicity of calculation, because we will be putting these values here, so we keep the power same, so it will be 18 into 10 to the power 9 Newton per coulomb. Now we will substitute the values of E1 E2 in this formula, so our E will become 9 into 10 to the power 9 whole square, 18 into 10 to the power 9 whole square, plus 2, 9 into 10 to the power 9, 18 into 10 to the power 9 into cos of 120 will be minus 1 by 2. So this everything is in square root. So the values will be 9 will be 81 into 10 to the power 18 plus 18 square will be 324, 10 to the power 18 minus this 2 gets cancelled. It will be 144 into 10 to the power 18. So 18 into 9 will be 144 144 or no 162, it will be 162. Now we'll add 81, 324 and subtract 162. So 81 plus 324 will be 5405 minus 162 will be 342, 243. So it comes out to be 243 into 10 to the power 18 Newton per coulomb. Now square root of 243, if you calculate square root of 243, it comes out to be, so 243 square root will be, so approximately 15.9, we can take 15.9. So it comes out to be approximately 15.9 into 10 power 9 Newton per coulomb. So this is your magnitude. Now you want to find the direction, because electric field is a vector quantity. So along with magnitude you should also find its direction. So direction is given by tan beta. Tan beta will be E1 sin theta E2 plus E1 cos theta. So E1, we have E1 is equal to 9 into 10.9, 9 sin 120 divided by 18 into 10 power 9 plus 9 into 10 power 9 cos 120. So it comes out to be 9 into 10 power 9 root 3 by 2 divided by 18 into 10 power 9 10 power 9 minus 1 by 2. So it will be 4.5 minus 4.5. So it comes out to be, this will also be, let it be like that. So 9 root 3 by 2 into 10 power 9, and in denominator we'll have 18 minus 4.5 will be 13.5 to 10 power 9. This, that gets cancelled. So you have 9 root 3 divided by 27. So it comes out to be 3. So 1 by root 3. So it comes out to be 1 by root 3. Tan beta is 1 by root 3. So beta will be 30 degrees. So in this case the angle comes out to be 30 degrees. Yes, so in this way we can find out the magnitude as well as direction of total electric field at point A. If there is a charge here, so the force will be, if the question says find the total force on a charge placed at A, you find total electric field and then just multiply it. So this is one of the kind of question which can also be asked. Next, very important kind of problem which can turn up in your exam is a charged particle of mass m and charge negatively charged minus q enters the region between the two charged plates. So there are two charged plates. One plate, let's say this is plate A and that is plate B. Plate A is positively charged while plate B is negatively charged. The charged particle, which is minus q and its mass is m, enters this region. This region is going to have electric field. Obviously electric field will be directed from positive to negative like this, and this electric field will be uniform. So this charged particle enters this region of electric field with velocity vx, and in the absence of electric field it would have traveled straight. But in the presence of electric field, since it is negatively charged, it will be experiencing a force in the upward direction. So the charged particle will move like this. We need to find out at the far end of the edge, that is here, what is this deflection. We need to find this deflection, and we have to show that this deflection at the far end or far edge of the plate is given by this expression. So to show y is equal to QE L square 2m Vx. This we need to show. So this question is extremely important. See guys, we need to follow CBSE rules. That is, we need to write what is given, and that is we need to follow steps. So there, because there is step marking in your CBSE exam, so it is better to follow steps. So we'll be writing everything that is given. Given charge minus q, velocity is equal to Vx along positive x direction, and then length is, this length of the plate is L. Now we know the gravitational force is extremely weak. So if you ignore the gravitational force, the only force which is acting on this charge particle is the electrostatic force. Because the electric field is directed downward, the net electric field will be acting upward. So the electrostatic force Fe is given by QE. The electric field is given E. So this force, we know Newton's law of motion, mass into acceleration equal to force. So the acceleration acting on the charged particle will be QE by m. Now the time taken by this charged particle to cross this length L, since the acceleration is, deceleration actually is acting or the acceleration actually, yeah, acceleration is acting along the y-axis. There is no force acting in the x direction. So the horizontal motion will remain unaffected because there is no acceleration or retardation acting in the horizontal direction. The force which is acting is only acting in the vertical direction. So the time taken to cross the region T is given by L by Vx. Now we'll use Newton's law of motion. You know, S is equal to ut plus half at square. So S in this case is y. Initial velocity, you know, initial velocity is v. So initial vertical velocity, since we are considering motion in the vertical direction, so in u vertical t half at square, u vertical initially is 0, half value of a can be taken from equation 1, which is QE by m, and t from equation 2, which is L by Vx whole square. So if you solve this, y comes out to be QE L square by 2m Vx square. So it is pretty straightforward. You just need to implement the ideas. The ideas are, if charge particle enters this region of electric field which is vertically, which is directed downward, there is no net force acting in the horizontal direction. So the time taken by the charge particle to cross this region will be L by Vx. The only force which is acting on the charge particle is along the vertical, ignoring the gravity because the gravitational force is very small. So the force which is acting in the vertical direction is given by the acceleration. The force is given by this, and then acceleration is this. So using Newton's law of motion, we can find this deflection. So deflection produced depends directly on the electric field and the length of the plate, and also inversely proportional to mass and square of the velocity. Yes, so it is very important question. Now, another important question is this. It says there is charge particle. There is a charge particle, capital Q, which is placed at the center of this square. So this is square, and then when you draw diagonals, the point of intersection is the center of the square. Here a capital charge Q is placed, and you need to find that a small charge Q, which is initially at B, it is moved from B to D. You need to find the work done in moving this small charge from B to D. So to find out the work done, what we need to do? So the work done is given by delta W is equal to Q V2 minus V1. We need to find what is initial potential and what is final potential. So we subtract the difference in potential, final potential minus initial potential, and then multiply by Q. So it turns out to be Vd minus Vb. Now you see, if the side of the square is A, then the diagonal will be A root 2, the total diagonal will be A root 2, and then the half of the diagonal will be A root 2 divided by 2. So A root 2 divided by 2. Now potential at B will be K Q by OB, which is K Q by A root 2 by 2, and potential at D is K Q by OA, that is OD, which is K Q by A root 2 by 2. What we see from equation 2 and 3, that potential at B is exactly same as potential at D. So point B and D lie on equipotential surface. So equipotential surface concept is extremely important. Questions, it is highly likely that one question will definitely be asked from this concept. So you know the work done in moving a charged particle on an equipotential surface is 0. So if you put 2 and 3 in 1, so put 2 and 3 in 1, delta W will become Q KQ by A root 2 by 2 minus KQ by A root 2 by 2. These two will cancel out and then work done will be 0. So it is concept of equipotential surface. Yes, so this is one of the question which can also be asked. Now we go for a different problem which is equally important. It says two spheres of radius r and small r and capital R have charges small q and capital Q on their surfaces as shown in the figure. They are connected by a conducting wire, and after the equilibrium is reached, like there will be exchange of charges, the wire is disconnected, and what we need to find out the change in energy. So to begin with, charges had initial, like spheres had initial charges, small q and capital Q, they had initial potential energy. So and different potentials. Now when the wire was connected, charge will flow from higher potential to the lower potential. So there will be exchange of, no, there will be transfer of charge from higher potential sphere to lower potential. Now when the equilibrium is reached, that means two spheres will have this common potential, same potential, the wires is disconnected. Now they will have their own different potential energy now. So what we need to find out, the difference in the final potential energy to the initial potential energy. So that will be the change in energy. So that we need to find out. So let us find out. So potential on sphere 1 V1 will be K Q1 by R1, and V2 is K Q by R, not R1, just R, and this is 2. So you have K Q1 by R, and then V2 is K capital Q by R. Now these two spheres, assuming V2 is greater than V1, so if you will be given values of Q1 and R, capital Q and capital R, you will yourself know which potential is higher. If you put the values and solve it, you will get the values of the potential which is higher and lower. So you know the charge always flows from higher potential to lower potential. Assuming V2 is greater than V1, then and let a small charge Q naught, not Q dash, flows from B to A. Therefore, new charge on A will be Q QA will be Q plus Q dash, and new charge on B will be QB is equal to Q minus Q dash. Yes. Now the initial, we had initial potential, and we'll also find out initial potential energy. So what is initial potential energy? Let us find out final potential and then we can find out VA. Let it be VA and this be VB, and assuming VB greater than VA. So VA dash, that is final potential, will be K Q plus Q dash by R, and VB dash will be K Q minus Q by R. Now since charges were on spheres, it is acting like spherical capacitor. So the energy stored in a spherical capacitor will be half CV square, right? So energy on spheres. So this is initial energy. Initial energy is given by Ui equal to half Ca Va square plus half Cb Vb square. Final potential energy will be given by half Ca Va dash square half Cb Vb dash square. Therefore, change in energy will be final potential energy minus initial potential energy, and it is given by half Ca Va dash square plus half Cb Vb dash square minus. So if you subtract these two, actually we can take the common directly, because we can subtract these two equations directly. So half Ca Va dash square minus Va square plus half Cb Vb dash square minus Vb square. We can substitute the values of Vb dash, Va dash, Vb and Va in this equation to find the actual change in energy. So if you put, the answer comes out to be half Ca Va dash is K Q plus Q dash by R minus K Q by R. It's square and then it's square plus half Cb K Q minus Q by R whole square minus K Q by R whole square. So this is a change in energy. What is Ca and Cv? Capacitance of A. Ca will be 4 pi epsilon naught R and Cb will be 4 pi epsilon naught capital R. So these are your capacitances. So you put these values, you find change in energy. So there will always be, if the potentials are different, you will always find some change in energy, because there is always loss in energy when there is make or break of circuit. Yes, so this question is important. If the values are given, you can find the exact values, VA, initial potential, final potential, initial, and then capacitance, and then you find initial energy, final energy, and you can find the difference in energy. So this is one of the very important conceptual question. The next important question which may be asked is, obtain the formula for electric field due to a long thin wire of uniform linear charge density lambda without using Gauss's law and by using Gauss's law. So this question will illustrate that using Gauss's law, a complex derivation like this, which we'll be showing using without using Gauss's law, can be very easily done using Gauss's law. So first we'll derive it using Gauss's law. First we'll derive it without using Gauss's law and then using Gauss's law. So the first part. So there is uniform wire, thin wire having uniform charge density. It's a long wire. We want to find electric field at this point, which is at a distance y. Assuming this to be origin, the wire spans from minus infinity to plus infinity. Assume a point charge. Let us take a very small part of this wire of length dl, which is at a distance x from the origin. So this point P will be at a distance of x square plus y square. We want to find electric field at P due to this charge distribution. So this small charge, this small portion of the wire will have small charge, so it will be lambda dl. Now electric field due to this will be along this direction, dE. Now we can resolve this electric field into two components. If this is theta, this will also be theta because it is vertically opposite angle, so it will be dE cos theta, and this one will be dE sin theta. Right, horizontal component will be will have cosine component, and then vertical will be sine component. Now if we consider a symmetrical portion on this side, then we can have dE, same dE at a distance x here. Suppose we take a symmetrical part of this wire on the other side of length dl at a distance x from origin. So this distance will also be x square plus y square. So the electric field will be dE. Now you'll have dE cos theta, and then here it will be dE sin theta. So you see dE sin theta, the vertical component cancel out each other. So what we are left with? Just dE cos theta. So dE net will be dE cos theta, twice of dE cos theta, and this is because of very small portion of the wire. Therefore E net will be integration of dE cos theta. This dE will be given by k dq by let this point be A, so AP square. So it will be k dq will be lambda dl. In this case it will be lambda dx because we are considering x-axis, so let it be dx dx. So it will be lambda dx by AP square. AP square will be x square plus y square. Now cos theta, if you see triangle POA, in triangle POA, cos theta is base by hypotenuse, so x square plus y square. So if we put these values here, so E net becomes 2 cos theta into dE. dE will be how much? It will be k lambda dx by x square plus y square, right? Now our limit of integration, since we are considering x and y, so x, since we are taking symmetrical length, we are integrating on the negative side as well as on the positive side, so there is twice integration. So our limit will be from 0 to infinity. All right, now to solve this integral, we'll do some substitution. Let x equal to y tan theta, therefore dx will be y sec square theta d theta. When x is equal to 0, theta is also 0. X is equal to infinity, theta is equal to pi by 2. So substituting this in 3, put 4 in 3, we get E net is equal to twice of, taking k outside, 0 to pi by 2 cos theta, lambda, we also take lambda outside, dx becomes y sec square theta d theta, and then x square plus y square. In place of x, we can put y tan theta, so it will become y square tan square theta into dx becomes y sec square theta d theta. Okay, now we'll take y square common. If we take y square common, we get 2k lambda 0 to pi by 2 cos theta y sec square theta y 1 plus, so this is 1 plus tan square theta d theta. Let's see, 1 plus tan square theta is same as sec square theta, so the sec square theta gets cancelled, y also gets cancelled, so we are left with 2k lambda y 0 to pi by 2 cos theta d theta. Now integration of cos theta is sin theta, so 2k lambda y sin theta 0 to pi by 2. Now we'll put upper limit minus lower limit, so this becomes 2k lambda y sin pi by 2 minus sin 0. So sin pi by 2 is 1, sin 0 is 0, this becomes 0, so we are left with 2k lambda by y. So this is our E net. Now we can substitute the value of k. K is 1 by 4 pi epsilon naught, so 2, this is 1 by 4 pi epsilon naught lambda by y, 2 gets cancelled, we have lambda by 2 pi epsilon naught y, so this is our E net. So that is how we solve this problem without using Gauss's law. Now we will be seeing what is the importance of Gauss's law. So we have uniformly distributed linear charge density. We want to find magnetic electric field at point P, which is at a distance y from it. What we are going to do, we'll draw a Gaussian surface, which will be cylindrical surface. Now we will use Gauss's law, which says total flux through the closed surface is q times 1 by epsilon naught times q enclosed. Now we'll have to see how much charge is enclosed in this cylinder. Let the length of the cylinder be L. So the charge will be, Q will be lambda into L. So this equation becomes lambda L by epsilon naught, which is E dot A. Now E dot area of this curved surface area of this uh, cylinder, will consider just curved surface area because the flux will be tangential to this surface, and then the angle is the area of this portion, and the direction of this area will be this, and then this is 90 degree. The flux will be 0 on the circular end, on that is on the either end of the cylinder. The flux which the net flux only will be possible, or like will be available to us only through the curved surface. So E into the area of curved surface of a cylinder is 2 pi r into L. This is lambda L by here the r, the radius of this cylinder is y, lambda L by epsilon naught. You see L gets cancelled, so electric field comes out to be lambda 2 pi epsilon naught y. So you see within 2 to 3 steps using Gauss's law you get the same result which you obtained without Gauss's law. So the importance of Gauss's law is huge in this case. You can reduce your problem in just to just a couple of steps. So it was one of the important question. Now we move to a next important question. This question was asked in CBSE 2016 as well as in 2020. The question says a charge is distributed uniformly over a ring of radius A. So there is a ring of radius A. We need to obtain an expression for the electric intensity at a point on the axis of the ring. And we also have to show that for large distance from the ring it behaves like a point charge. The ring distribution, the charge on the ring distribution behaves like a point charge. So the diagram looks like this. So there is a ring, circular ring, and it has got uniformly distributed charge on it. Its radius is A, and we need to find electric field on its axis. Let us consider any point P on this axis. We'll consider just like we did here, we'll consider a very small portion of this ring dl, and we'll have very small charge dq. Electric field on this point P will be pointed towards this dE. And then if this angle is theta, this is also theta. So this dE will have two components, dE cos theta, horizontal component, and dE sin theta, the vertical component. As we saw here, the cosine we can have another symmetrically opposite portion for which this will be dE, this is theta, and then you have dE sin theta, and this is dE cos theta. We see this sine component cancels each other. So while we'll integrate over the ring, the sine component will cancel each other and we'll only have the cosine component. So in this case, the dE net is dE cos theta. If we take 2 dE cos theta, our integration will be over pi r only, because if you are taking 2 points, the integration will be just half of the circumference. But if you are taking just 1 point, then you need to integrate over the whole circumference. So if you take 2, because we have dE cos theta and t cos theta, this is 2 dE cos theta. So your dE will be k. What is your dq? Dq is lambda suppose charge q is there, so your lambda will be q by 2 pi a. So dq will be lambda dl, which is q by 2 pi a into dl. Therefore dE will be k dq by Let this point be P, this point is AP square. So it is K Q by 2 pi A dl. AP square is, this distance is x, so this is x square plus A square whole square. So our dE becomes K Q by 2 pi A dl by x square plus A square. Now we'll plug in this value here. We'll put 2 in 1, put 2 in 1, dE net becomes 2 K by 2 pi A Q dl by x square plus A square. Cos theta. Cos theta will be based by hypotenuse, so x by x square plus A square. Now to find total electric field, we need to integrate it. So E net will be dE net 0 to E, and it will be integration of 2kq 2 pi A x square A square 3 by 2 dl, and the integration is 0 to pi A. Because why pi A? Because we are taking 2 points for integration, and while you sweep this, while you integrate this, you need to just move half of the circumference to complete the whole ring. That is why the integration limit is 0 to pi A. So you may cut this 2, so it is kq by pi A x square A square 3 by 2 dl. Integration will give you a 0 to pi A. It becomes kq by pi A x square A square 3 by 2, and then integration will be upper limit minus lower limit. Now this pi A gets cancelled, so your net electric field becomes kq by x square is A square 3 by 2, right? There is extra x here which was missing, x. So this is a E net. Obviously this is directed towards OP. Now at far distance, at very large distance, you want to find electric field for very large distance. So these are special cases. If x is greater than A, then E net will be kqx divided by x square 3 by 2, because we ignore A. So this becomes kq by x square, which shows the distribution behaves like point charge. Why this equation shows that distribution behaves like a point charge? Had the charge been a point at O, and you want to find electric field at any other point, the electric field will be kq by x square. So for a large distribution, like for a large distance, the distribution looks like a point charge. This is the conclusion. Now another special case can be at the center. If x is equal to 0, electric field, you put x equal to 0, electric field becomes 0. So at the center of the ring, electric field will be 0, because the charge is symmetrically distributed. Electric field gets exactly cancelled out at the center. Yes, now we move to current electricity, the next chapter, which is the next chapter. And here in current electricity, the most important topic is Kirchhoff's law. So we'll start with Kirchhoff's rules. So question will be like this: find the current in each of the following branches. So branch assume a loop looks like this, like a circuit looks like this. The nodes are this A, B, C, D, E, F. We take this as 10 volt, any random value, 5 ohm, 6 ohms, and here maybe 10 ohms, and this is 5 volt. Now we'll use two laws. We need to find current. Current I1 flows in branch AB. Here I2 is flowing, and in this BE I3 is flowing. We need to find currents I1, I2 and I3. Now using Kirchhoff's rules, number 1, junction law. At the junction B. So junction law says the total incoming current is equal to total outgoing current. Junction law also states that, like, junction law is as a result of law of conservation of charge. Total incoming charge is equal to total outgoing charge. So the total incoming current is equal to total outgoing current. So you have I1 plus I2 is equal to I3. This is equation 1. Now using loop law, you all know that loop law is as a result of law of conservation of energy. So we'll use loop law in loop A, B, E, F, A and B, C, D, E, B. So in using loop law, in loop A, B, E, F, A, we assume clockwise to be positive. So 10 volts is equal to 5I1 plus 6I3. Now in loop D, C, D, E, B, let us assume anti-clockwise to be positive. So 5 volt, because this battery, this cell is sending current in anti-clockwise direction. So this cell potential will be positive. I2 is also going in anti-clockwise direction, so it is also positive. I3 is also following the same trend. So it will be 10 I2 plus 6 I3. Now we have 3 equations and 3 variables. You just need to solve it. Solving this, you can find I1, I2 and I3. So that's how Kirchhoff's rules can be used to solve for values of current in different branches. Let us solve this. What we are going to do is, we'll substitute the value of I3 in equation 2 and 3. We'll put equation 1, that is, we put I3 from equation 1 in equation 2 and 3. So equation 2 becomes 10 is equal to 5I1 plus 6I2 plus 6I3, which is 6I1, right? So it becomes 11I1 plus 6I2. Here 5 will be equal to 10I2 plus 6I3 plus 6I2, 6I1 plus 6I2, and then it will become 6I1 plus 16I2. So now we have equation 4 and 5. These are 2 equations in 2 variables. Now you see, you have 6I2 and here you have 16I2. Which variable we want to reduce, like eliminate? So we can multiply it by 16 and here by 6. So if you multiply 16 and 6, what are you going to get? 160 is equal to 16 into 11 will be 16 minus 16, 16 minus 17, 81, 16 6 are 96 I2. Here 30 is equal to 36 I1 plus 96 I2. Now if you subtract, this gets eliminated and we have 130 is equal to 0, 4, 140 I1. So what is I1? 130 by 140. So it is 13 by 14 ampere. So we could find I1. Now we'll put this I1 in equation 4 or 5 to get I2. So put 6 in which equation? 4. So 10 will be equal to 5 into 13 by 14 plus no, it's 11, right? 11 into 13 plus 6 I2. So 6 I2 is equal to 10 minus 11, 3 by 43, 11, 14, 143 by 14. So if you like solve it, 140 minus 143 will be minus 3 by 14. So your I2 will be minus 3 by 14 into 1 by 6. So minus 1 by 28. This negative sign shows that your chosen direction, this chosen direction is not the correct direction. Actually, I2 is flowing in this direction, just the opposite direction. If after solving Kirchhoff's problem, you are getting your current to be negative, that only means that current is flowing in the opposite direction of the chosen direction, of your direction. So in this circuit, current is actually I2 is flowing in from B to C, not C to B. Now we have I1 and I2. We'll put these values in equation 1 to get I3. Right? So put 6 and 7 in equation 1. So I3 will become 13 by 14 minus 1 by 28. So it will be 26 minus 1, so 25 by 28 amperes. Therefore, currents are I1 is equal to 13 by 14 ampere, I2 is equal to minus 1 by 28 ampere, and I3 is equal to 25 by 28. So this is how you need to conclude your answer. In every question you need to write like given, and then after solving you need to conclude your answers. Remember, CBSE has got step marking, so you need to follow these steps to get marks. So this is how we solve a circuit problem using Kirchhoff's rules. The next type of problems that you generally get using in current electricity is a problem based on Wheatstone bridge. So the loop would look like this. So a loop would look like this. So in this loop, you need to find the current flowing in the circuit. So let current I is flowing in the circuit. You clearly see that this is a balanced Wheatstone bridge, because this is 5 ohm, this is 10 ohm, 5 by 10 is equal to 20 by 40. So in this question, we'll not only find current, overall current in the circuit, but we'll also try to find current in each branch. So we'll try to find current, overall current in the circuit. At the same time, we'll try to find current in each branch. Now you see, this is a perfectly balanced Wheatstone bridge. So you know, in a perfectly balanced Wheatstone bridge, no current flows through the galvanometer. So this resistance will be out of the circuit. So equivalent circuit that we can draw from it is this. Now see this, since no current flows through this 10 ohm resistor, this point and that point is at the same potential. That means this is not in the circuit. So the new circuit, or equivalent circuit, looks like this. Now you see these two resistances are in series and these two are in series. Together they are in parallel. So the equivalent circuit now looks like this. This is 15 ohm and that is 60 ohm. Now these two are in parallel, so equivalent resistance will be 15 into 60 divided by 15 plus 60. That means 15 into 60 divided by 75, 5, 12. So this is 12 ohm. Now 12 plus 16 total resistance, how much it will be? It will be 18 ohm. So 18 ohm and you have 10 volt. So what is current, overall current in the circuit? We'll use Ohm's law. So V equal to IR. What will be your I? V by R, which is 10 by 18, 5 by 9. So total current in the circuit is 5 by 9. Now, another crucial question which is generally asked is, what is current in each branch? So let us look at this diagram. You have I, which is 5 by 9 ampere. Out of 5 by 9, what fraction will go through this and what fraction will go through the 60 ohm resistance? So the formula for that is, suppose you have R1 and R2 resistances in parallel and current I is flowing. If this is I1 and that is I2, so I1 is given as R2 divided by R1 plus R2 into I, and I2 is given by R1 by R1 plus R2 into I. So this is formula for current in each branch. Now using that formula here, suppose this is I1 and this is I2. So I1 can be calculated as 60 divided by 15 plus 60 into 5 by 9. So it will be 60 divided by 75 into 5 by 9, which is 4, 5 again gets cancelled, 4 by 9 ampere. So if out of 5 by 9, if 4 by 9 flows through this, so rest of the current will flow through this. So I2 will be how much? 5 by 9 divided by 4 by 9, that is 1 by 9. So overall current, it is 5 by 9, here it will be 4 by 9 ampere and here 1 by 9 ampere. So that's how you calculate current in each branch. This question, we need to find the total resistance of this cubical network across one of its body diagonal. Now we see this cubical network is very symmetrical. The first three are together in they are connected between the same potential. So first three are in parallel, last three are also in parallel, the rest of the 6 are together in parallel. It can also be realized if you stretch this cube across the diagonal, you'll find 3 here, 3 there and 6 in between. So you can draw the equivalent potential, equivalent resistance like this. So first three, last three, first three are in parallel, last three are in parallel, and then the remaining 6 which are in between, they are also in parallel. So suppose each of them having the same resistance R, and R. So these 3 in parallel will yield you R by 3. This 6 will yield you R by 6 and then again R by 3. So you get 3 resistances connected in series. So R by 3, R by 6 and R by 3. So if you add them together, it will be 2. So you add R by 3 plus R by 6 plus R by 3. LCM will be 6. 2R, R plus 2R. So total resistance will be 5 plus 6. So equivalent resistance in this case comes out to be 5R by 6 ohms. Given R, suppose R is 1 ohm, you can find 5. Like whatever value of R will be given, you can just put the value of R and find the equivalent resistance. Alright. So in this question, we want to find the overall current in the circuit and potential difference across the terminals A and B, or the points A and B. To find total current flowing in the circuit, we need to find the equivalent equivalent potential of this connection. So we'll use cells in parallel. So we know E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2. Since these two resistances are in parallel, so R equivalent for this resistance will be R1 R2 by R1 plus R2. So it is 1 into 2 by 1 plus 2, that is 2 by 3 ohm. So this equation becomes 2 by 3 equal to 5 by 1 plus 10 by 2. So this is 10. So E equivalent becomes 10 into 2 by 3, which is 20 by 3 volts. So E equivalent in the circuit is how much? 20 by 3 volts. Now this circuit can be redrawn as like this. Now this volt, this is 20 by 3 volt and this is 2 by 3 ohm. This potential is 2 volt and 1 ohm. Now you see, this potential is sending current in anti-clockwise direction, but this battery is sending current in clockwise direction. They are opposite to each other. So what will be the total equivalent EMF? Since 20 by 3 is greater than 2 volt, so overall current will be in anti-clockwise direction. Right? So equivalent E total will be 20 by 3 minus 2, which is 14 by 3 volt. And the total resistance will be 2 by 3 plus 1 plus 5. So R total will be 2 by 3 plus 6, 1 plus 5, 1 plus 5, that is 2 by 3 plus 6, 20 by 3 ohms. Now this circuit can be equivalently drawn as like this. The total potential is 14 by 3 volt. Total resistance is 20 by 3 ohms. What will be current in the circuit? Therefore, current in the circuit will be E total by R total, which is 14 by 3 divided by 20 by 3. 3 gets cancelled, 7 by 10. So total current 7 by 10. So what is total current in the circuit? 7 by 10. And this current is flowing in anti-clockwise direction. So this was the first part of the answer. Now the second part is we want to find what is potential difference between the terminal A and B. So we'll draw A and B like this. The current I 7 by 10 ampere flows through it. This is 2 volt and this is 1 ohm. Now how to find potential difference in such cases?
माइनस हो रहेगा माइनस 7 by 3 कैसे
7 by 10
7 by 10 ये 1 ohm माइनस में हो जाएगा प्लस 2 वोल्ट ये इक्वल टू 0
माइनस में हो जाएगा
हाँ प्लस में जाएगा
plus. So you see, to find out total potential difference in this cases, there are two cases like this. First is when current is coming out of the cell, and when current goes inside the cell. In this case, when current comes out of the cell, the terminal potential difference VAB, when current comes out of the cell, that means battery is sending current, battery is driving the current. So in that case, the potential decreases. So it will be V minus IR. But when current goes inside the cell, that means battery is getting charged. Alright, it is receiving current from outside. In that case, what will happen? VPQ becomes V plus IR. Potential gets added. In this case, the current goes inside the cell. So what will happen? What will be the potential difference? What will VAB? 2 plus 7 by 10 into 1. So it will be 27 by 10 volts. So this is your answer. This portion is very important. This is generally asked in CBSE exams and also in JEE and other competitive exams. From CBSE exams, from CBSE point of view, this concept is extremely important.